This is the video for Mod 5 Lesson 1, Solving Systems of Linear Equations by Graphing. The goal of this topic or unit we're going to be starting is really revisiting some of the topics for solving systems we saw back in Math 1, and then adding some questions that are similar to system problems you can see on the SAT. So our goal for this section is to identify solutions from a system from a graph, but also to solve a system by graphing. So the first topic is going to be identifying a solution from a graph. Just a reminder, a system of equations, and there's an example down here, is a set of equations. Typically we have two equations, two variables, and we're looking for values of x and y that satisfy both equations. So a solution, you'll have a value of x and y that would work for both equations. So an ordered pair that satisfies this equation it is going to be a solution, and this represents really the intersection on the graph. So the goal is we're really just graphing these equations and seeing where they intersect on the graph, and that's our solution. One situation we can have is if they intersect at only one point, and we can see like in this example here. So we have the equation y equals 2x minus 1. We also have the equation y equals negative x plus 5. They actually intersect at the point 2, 3. So what that means is that's the solution for this system. So if I was to put in for x the number 2, for y the number 3, you wouldn't have to do this for every problem, but just so you can see, it actually would work out for both equations. And so that would be a solution to the system. Two other situations we can have, and you might remember these from Math 1, is you could have infinite many solutions, or you could have no solution. So infinite many solutions, if we look at this system, you might not recognize it's infinite many right away, but if you were, let's say, to graph this line using intercepts, or if I was to just kind of visually write this in slope-intercept form, but you could have graphed it with intercepts too. You would actually see that these are the exact same equation. So infinite many solutions means that they share all their points in common. So there's many, many, many solutions. We can't list them all. That we call that a dependent system. And so anytime you have it where they're the same exact line, you would write infinite many solutions. An inconsistent system is one that has no solution. So if you're looking at graphing it, you might notice both of these have the same slope. When we graph it, you get parallel lines. So that would be an example of no solution. So anytime you get parallel lines, you're going to have a no solution because there's no point that they intersect at all. So those are like your three different scenarios you could have. So the steps we're going to be using for graphing are we're going to graph each equation either in slope-intercept form or with intercepts. We're going to graph them on the same coordinate plane and check their point that they intersect, and or estimate the point. And then if we can check it algebraically, if we're not sure, we can do that to substitute it in if we're not quite sure where that intersection is taking place. The first example here, we have these both in slope-intercept form. And so what we're going to do is first identify the slope and the y-intercept. So in this case, for the first one, our slope is -1, our y-intercept is -2, and in the second one, our slope is 2/3, and our y-intercept is 3. So remember, when you're graphing, you're always plotting your y-intercept first, like we've been doing for other graphing, and you might remember from Math 1 and Math 2. And so for this first one, I'm going to plot it at -2, that's our y-intercept. And I'm going to go down 1 over 1. I might do that a few times. I might go in the other direction too, just to make sure, because again, the intersection is our solution. So if you have a straight edge, you would just use a straight edge. And so I'm going to plot this in a moment. I'll go like this. Okay, for the second one, same thing. I have it at 3, so I'm going to go 1, 2, 3. And then I'm going to go up 2 over 3. Up 2 over 3, so I'll do that maybe a few times. I might go in the other direction too, because I see that's probably where my intersection is going to take place. And I can see that this system is going to have a solution. I can see that they intersect at actually this point here, negative 3, 1. If I wasn't sure, I could substitute it in to make sure that that works as a point. So if I wanted to check it, I can. So the opposite, negative 3 minus 2. And does it work for the other one? And it actually works for both. So our solution for this is negative 3, 1. For the next example, you can do this a few different ways. You can graph this with intercepts. You can graph this using slope-intercept form. It's completely up to you which one you'd like to do, right? So for this problem here, if you want to graph with intercepts, you can. If you want to graph with slope-intercept form, you can too. I'm going to graph with slope-intercept form just because we haven't seen that in a long time. We just did a lot of stuff with x and y intercepts. But it really doesn't matter which one you choose to use, right? I'm just going to do slope-intercept form because we're maybe a little rusty getting y by itself. But intercepts might be a little faster with graphing. So if you chose to do it with slope-intercept form, you would get y by itself. Divide by negative 2. So we have here 3/2 x plus 6 as our first equation. Our second equation is still up here, negative 2x minus 1. And then we're going to go ahead and just graph it out. So this, and again, this I just got in slope-intercept form, but you might have just graphed it using intercepts too, and that was okay. That might have been even a little faster. So if I graph this one down here, I'm going to start at positive 6. 1, 2, 3, 4, 5, 6. And then I'm going to go up 3 over 2. And I might do the same in the other direction too, so down 3 over 2. Okay, and then we're just going to do our best to connect it. And then do the same with the other equation. So negative 2x minus 1. Our y-intercept is negative 1. Our slope is negative 2. And so we're going to go ahead and start at negative 1. Go down 1 over 2. Or down 2 over 1. And then I might go in the other direction because I see that's probably where I'm going to have an intersection take place. And I actually do have an intersection. It's at the point negative 2, 3. And if I wasn't sure, I could always check my answer. So if I was to put negative 2, 3 into this equation here, it actually checks out. And if I put it into the top one up here, it also checks out. So our solution for this is going to be the point on negative 2, 3. So x is negative 2, y is positive 3. So that's your x and your y. If you have questions from the notes, please make sure you're asking questions in class, during T-Bolt time, or in the center. You do need to complete the U-Tries to receive full points for these video notes. So when these are checked in class, you do need to make sure you have your U-Tries completed to receive full points. So again, the remaining problems from this section need to be completed. Even if they're not perfect, we need to see that you're trying the steps out before you come to class so you're ready to ask questions. All right, thank you very much and have a great rest of the day.